We good? Everyone's good? All right, we need one more restriction on z to get our bounds, right? So when you look at this solid tetrahedron, the bottom of it is the xy plane, which is just z equals 0. So we know z is bounded on the bottom with 0. What is it bounded on the top with, though? A plane, right? It's this plane right here, which we are not, that's a question mark? We are not given the equation of that plane, are we? So we have to get it, right? We have to actually go get it. And how do we get the equation of a plane if we're given 3 points through the plane?
Like you can cross them.
You create vectors and then cross them. That gives you your normal. And then you use one of the points. Exactly. So we actually have to go do that before we can continue. Understand? Yeah, it was this semester. We did that, if you believe that or not. All right, let's do it. So let's create a vector. I did this problem right in between classes. I was just sketching out, just to make sure I had looked at it before class. And I accidentally took my vector from this point to this point initially. I was like, wait a minute, hold on, that's not even on the plane. It has to be on the plane. So I'm going to do a vector that goes from here to here, and a vector goes from here to here. Do y'all agree those two vectors are on the plane? I chose to start at the origin because how do you find the vector that goes from here to here? From here to here, you take this and subtract those, right? And then just create a vector out of that, and then here minus that. And if I use the origin as my starting point, when I subtract 0, 0, 0, nothing happens. So let's see, my two vectors are, I'll just call them v1 and v2. The two vectors, the first one is the vector 0, 1, 1. These are vectors, not points now. And vector 2 is the vector 1, 1, 0. And then you have to take their cross product, right? So when we cross them, that'll give us our normal vector. And let me do that real quick. Cross product, cover those up. Do your determinant over here. You should get -1. Cover up the middle. Do your determinant. You should get -1. But then you have to change the sign. So it becomes +1. And then you do the last part. You get -1 again. That's your normal vector of the plane. Once you have the normal vector, all you need now is a point. And then you can, oh, did I forget the one? Thank you for laughing at me. That helped me see that I made a mistake. Okay, -1. Now, my equation. So I put -1 in front of x minus, and I pick any of the points on the plane. So I think 0, 0, 0 is the best one to pick, right? Because it's easy to work with. So 0, and then I have +1, y minus 0, and then -1, and then z minus 0 equals 0. That's just to remind you I'm using the plane equation where this is a, b, and c. That's your normal vector components, a, b, c, and then the 0, 0, 0 is one of the points. And this just turns out to be -x plus y minus z equals 0. And that is the equation of that plane that's forming the top surface. What do I need to do with this? Solve for z. So z is equal to -x plus y, and that goes right here, -x plus y. That's my upper limit on z, is that plane up top. Set up the triple and we're done. At least we're done with the setup. So the triple will be all right, 0 to 1, 0 to 1, and then 0 to y, and then 0 to -x plus y, and we're integrating xz, and then what's my order here? zxy. Good, good. zxy. Do you think it's possible to type that into like Wolfram Alpha or something? Right? You can do like a nested integral, an integral within an integral within an integral. It'll do it, and it'll take it, and it'll give you a numerical answer. Do y'all want to see it, or? You got time? All right. Well, I mean, I guess it won't hurt, huh? Okay, so first, you'll see what I'm hitting here, right? This one, and then inside the integrand, I hit it again. And then inside of that, I hit it again. And I'm going 0 to 1. Oh, that didn't work. Why is my caps lock on? 0, tab, 1, tab, 0 to y. 0 to negative x plus y. And here, x times z. X times z. I always like to put a multiplication symbol in between, because some computer programs will look at xz as like the name of a variable, like together. It's weird. Certain programs do it. And then we're going z first, then x, then y, right? Oh, we got it already. Okay, there it is. 1 over 120. Okay. So, and that, again, could represent different things depending on the application. All right. What's next? What do you think's next on the ground? XZ. How do you mean?
As in, we've got.
Okay, let me silence this. My wife apparently doesn't know that I'm at work.
Tell him we said hi.
Yeah, she's mowing the grass right now.
Could we have z be valued between two constants, and then x be a function of y, and y be a function of x and z?
Yeah, see, exactly.
I mean, thinking on, you could do literally any combination of those. Could we also have x and y, like two of them both be functions of?
Can't have them both functions of 2. You have to have, so here's what we've had so far. We've had x between two constants, right? Y between two functions of x, and z between two functions of x and y. We've also had y between two constants, x between two functions of y, and z between two functions of x and y. We can do this for any of the 3 variables. So I could do this. I could do z is between two constants, right? Let me go R and S. And then I could let the x be between two functions of what? Z. And then I could let the only variable left, y, be between two functions of what? X and z. Right? Or you could have switched these two and put the x between two constants, the z between two functions of x, and then your y between. You see there's all these different combinations?
Like a step down, like a little bit?
Pardon me?
As long as you do like a step
Yeah, as long as one depends on the other and the other depends on that one. So you know how the ones I've shown you so far, we were looking like a light from the top and it was casting a shadow on the xy plane? Your solid could be where you're casting your shadow on, let me do it this way. Let me bring this out again. So if I have my solid in here, right? If I have my solid in here, what we've been doing is we've been casting a light down in the shadow on the ground. It's our two-dimensional domain. It was either type 1 or type 2 down there. But we could have a light source shining this way and casting the shadow over here onto this plane.
So there's 6 different combinations.
Yeah, so how many do we have, right? Here, we have 2 different ways of doing it, right? Type 1, type 2 down there. If we go this way, up against here, we have 2 different kinds, type 1, type 2 here. and then we could shine a light this way up against this plane and have type 1 and type 2 shadow on there. So there's a total of 6 different triple integral type situations we could have here. Now, I'm not going to test you on all of them to make sure you know how to do them all right? You just need to know, that you can. So let's see where the next note takes us here. So this is one particular example out of those 6 possibilities. Y is between 2 constants. Z is between 2 functions of y. And the x is between 2 functions of x and of y and z. Let's see, before I show you the picture, see if we can wrap our heads around this. X, y, z. So the y is between 2 constants, right? The z is between 2 functions of y. So you have the y is between 2 constants, like this, and then your z values are between 2 functions. So this is our shadow over here. Y is between 2 constants, z is between 2 functions of y, and the x value is stuck between 2 surfaces out here. So you have an x surface here and an x surface here. Shadow being cast this way. There it is. That's the same thing I was just trying to show you. Y'all see the shadow over there? Let me see if I can shadow. There's the shadow. That's the y, z plane. And the solid comes out towards us in the x direction. The triple integral for that setup would be the restrictions on y first, and then your 2 functions of y that give you your z value, and then your x values are the surfaces. So this is an exercise for your own. I'm not going to do this. It's the same problem we just did. But I ask you, instead of taking that tetrahedron and casting the shadow down on the ground, cast the shadow on the YZ plane, and then try it with casting the shadow on the XZ plane. Yes?
I feel like every problem we've covered after the midterm has been super time consuming. How will the final exam go with all these long problems?
Set up, don't evaluate. Yeah. Yeah.
Not going to complain about that.
Yeah. Pardon? Yeah, we just want to get it to the integral. And then once we get it to the integral, yeah. But I'll be completely honest with you. This is we're still doing very trivial stuff here because we haven't started doing vector fields and where we have vector functions. Well, trivial in the sense that we're integrating scalar functions. These are scalar functions. Everything's nice. Everything behaves the way it behaved in Cal 2. Nothing is out of the ordinary yet. So it is, maybe trivial is not the word. Trivial is maybe like 1 + 1. This is not trivial. It's just, on the final, I'm going to ask you problems that are different than this, but it's like if you can do those problems, then this would have been no problem for you to do anyway. It's like, well, it's the problems later, I think, are much more, take deeper thinking than this. So my idea is that if you can do those, then these, if I would have asked you these, would have been no problem. So it's going to be hard to make a final because there's so much material. And, but the test is longer, right? It's almost 3 hours as opposed to our in-class test that was the midterm as 1 hour 40 minutes, right? So the final is going to be 1 hour longer than our midterm was. So I can ask you more, right? Just do the one Lagrange problem? Yeah.
We could spend 3 hours.
All right. So
Lagrange were the longest ones that we've done.
look at this one here. Evaluate the triple integral over E of Z with respect to volume, where E is the solid bounded by the cylinder y squared plus z squared equals 9. Okay, let me just wrap my head around what that is. Y squared plus z squared equals 9 is a cylinder of radius 3 that goes out which axis? Goes out the x-axis because x isn't here, right? So I had this circle of radius 3 that comes out this way and goes that way, right? So you got this cylinder. And then I have some planes. X equals 0. It's ground, right? So now I've got my cylinder coming out here, and then I got this plane cutting through it. Y equals 3x. No, let's do z equals 0. Z equals 0 is what? Wait, what did I just say? X equals 0? I said that was the ground, didn't I? Yeah. I meant to say z is 0 is the ground. X equals 0 is what? This wall. So I've got this wall, this right here, and the cylinder coming through. And then I have this y equals 3x, which is a line in two-dimensional space, right? It's a line down here, but in three-dimensional space, it's a plane that goes straight up like this. I think I might try and draw it. Yeah, because I didn't show a picture of it. And we're in the first octant, right? We're in the first octant. All right, cylinder coming out at us. Going down the z-axis, right, and down the x-axis. Got a cylinder that has a radius of 3. I've got the ground, and then I've got the back wall. So at the back wall, it creates that, right? Nah, not like that. This picture's not very good. It goes around the back side, doesn't it? Yeah, like that. Where else is it cut?
Down the middle.
Yeah, like the bottom. Okay, so I'm trying to redraw this over here, okay? Because this is just for me to kind of sketch. I've got basically the top half of the cylinder to the back like this. You all see that? Right, the back, the bottom. Now that cylinder keeps coming, right? It keeps coming out. But I'm cutting it with this as well. Y equals 3x. What does that look like? Over here on the ground, what does that look like? Here's x, here's y. What does y equals 3x look like? If you go out 1, you're up 3. Like that. It's a line like that. So if I go out x1, my y value is out here 3. Hey, that's the radius, isn't it? 3. So I go out 1, it goes out to 3 there. It cuts through there. And cuts up, doesn't it? Wouldn't it do this? It's like a wedge. It's kind of weird, like when you're trying to put all this together. This is a little harder than a box, right? It's a little harder than a box. So my cylinder came out, right? I had the ground, the back wall, the ground, the back wall, and then I had this plane that came through and went whoosh, like that, and it cut back here and created that wedge back here. Yeah, something like that. You got it or no? Kind of? Can't draw it, but...
Yeah,
You only needed like the first octant and then y equals 3x, right?
yeah, we only need the first octant.
Like x equals 0 and c equals, that's not relevant.
X equals 0. X equals 0 is important for the back wall of the wedge. Oh, you're saying first octant. First octant. Oh, that's to eliminate the back side of this. Because, right, the cylinder actually goes on the other side. When I say x equals 0, I'm not telling you which side of 0, right? So the cylinder extended to the back side, which means there's another wedge on the back side of this. Like, you know, this wedge is over here. There's another wedge over here where that line comes through like this, right? There's another wedge on this side. So to eliminate this back side, I just say, hey, look, we need to be in the first octant. All right. Yes.
So in these problems, technically we're going above 3D, so we can't.
Wait,
really-
technically what?
We're going above 3D, right, in this sense?
Above
Not-
3D?
Not the domain, but like the functions that we're dealing with.
Yeah, the function is in fourth dimension.
Right. So we can't just assume symmetry like with the function.
Oh yeah, you don't necessarily have symmetry here. Unless you can convince yourself that that's symmetric.
Like it's an even odd function or something like that?
It would have to be with all the variables taken into account. Yeah. Well, do y'all see the wedge? Anyone have a question on this wedge? How are we going to define it? Like, are we going to say this is like our x is between two constants, our y is between two functions of x, and our z is between two surfaces that are functions of x and y? Or do you want to project the shadow? Which way do you want to project the shadow, I guess is what I'm saying. Do we want to project the shadow down, up against the back wall, or do we want to come this way with it? Does that make sense? Because we have 6 options on how to do this. Down? Down, because the bottom is a triangle, right? Now, what if I projected this way? What would the shadow be? Half a circle, which means I would probably want to use polar coordinates, right? Yes?
How's it half a circle?
Well, I said half, I meant quarter, sorry. Half and quarter, same thing. You know what I mean? You know what I mean, right? Quarter circle, right? Quarter circle.
I'm remembering that, I'm just gonna equate those now.
Yeah, there's a half and quarter of the same thing. I don't know who told you something else. Get it straight. All right. I think I'm going to go with that picture. All right. So let's see. What is our domain on the ground? I'll do a better picture of our domain on the ground. We are choosing to project the shadow down. So when x was 1, y was 3, right? And it goes like this, right? We have to be careful there. It's not this side. It's this in here. I think I'm going to stick with type 1. All right, our x's are between two constants, right? X is between 0 and 1. What are our y's trapped between?
1/3 x.
Yep, right here. Yeah, so you need to, well, what's the slope of this? Isn't that just y equals 3x? Right? I think you were doing it as a function of x, not y. So the bottom of this is y equals 3x. That's the bottom. And the top is what? The constant 3 function, right? 3. The bottom edge of that is 3x. Yeah, so what's the z, right? What's the z? Well, the z, what's the bottom bound of this thing? What's the bottom? Z equals 0. Okay, and what's the top? Well, it's this thing, right? Which is that solved for z. And when you do that, you can get a plus or minus, aren't you? When you solve for z, well, we're talking about the top of the cylinder, not the bottom. So we'll only want the positive answer. Make sense? So solve that for z, and you should get square root of 9 minus y squared, right? Y squared. So just take that, move that over, take the square root, only take the positive root. There it is. Well, that's the bounds. Now we need to set up the actual triple. So the triple is going to go from 0 to 1, and then it's going to go from 3x to 3. And then it's going to go from 0 to the square root of 9 minus y squared. And we're actually integrating this function z, and we're going dz, dy, dx, because I chose to put these restrictions and look at it with the shadow projected that way, and to look at it as a type 1 on the ground. And did I do this on the computer? I don't think I did. No. What do y'all think? Is it making sense to y'all? Like, the drawing of the pictures might start to become a little bit of an issue, all right? Which, I remember when I took Cal 3, man, it was brutal. We had no technology, no, hey, look at this, spin this around, look at it from this point of view. And my professor was not very good at drawing. I'm not claiming I am, but he was way worse than this. And I just sat there going, what the hell is going on here, you know? So it took a while for me to get comfortable with drawing things, and it should take you a little while too to get comfortable with it. It's not a thing we're just automatically start and we're just automatically good at it. So take your time with it. All right, triple integrals. Yeah, my Cal 3, it was bad. But I also had him for graduate linear algebra in graduate school. So there's linear algebra undergrad, and then there's linear algebra when you're graduate school as well. I had him for that. He's fantastic. So he was really more of a higher level teacher. The Cal 3, I think he was just doing kind of like on the side. I don't know, but his 3D drawing wasn't that great. All right, so this is what we were talking about just a second ago. There's a bunch of different scenarios. We're not going to go through all of them, all right? All right, big application here. Big application. When we were doing, what? When we were doing double integrals, there was a formula at the end I wanted you to put a star next to. It said that if you were doing the double integral over d of 1 dA, that this is the area of d, right? And I actually used that to prove something to us. What did I prove? The area of a circle. And I used polar coordinates to do it, right? So I used that formula to prove the area of a circle in this class. This says that if you do the triple integral over e of 1 dv, that means that function that's in that other dimension, all it's doing is multiplying all the values together. I'm sorry, it's how do I say this? It's like a hyper, it's adding up all of the values, right? Each one. Maybe I can do it this way. It's hard to explain because of this. Look, here on the ground was our domain D. And so if the height of the function above was 1, right, if that distance from here to here is 1, then the volume of this, the volume of that solid, is numerically equal to the area of D. That same principle here. If we have some solid in three-dimensional space, this is our domain E, and now this is the constant 1 function, then the, what do you call it? See, like this area times that height gives you volume, right? But what is this volume times its height? See, we're in four-dimensional space now, right? So what is it? I don't know. We call it a hypervolume. It's just up one dimension higher. That hypervolume, the numerical value of that hypervolume is equivalent to the volume of E. So, yeah, we're going to use that later, all right? Last example, we're done with this section. Find the volume of the solid bounded by the cylinder, y squared plus z squared equals 9, in the planes. Wait a minute, is this the same problem? Is this the same problem I just gave you? Yeah, no. Look at the problem we just did. I said evaluate this triple integral over e of, look at our scalar function here, z dv, right? And then we set up the integral. We didn't do the work, right? But we set up the integral. And we didn't do it. We just left it there. Now, the next problem is saying, you know what? Give me the volume of that solid, that wedge. Yes? Yeah, so we're going to use the same setup with that wedge. Right? There's our little wedge. It's the same exact limits of integration. 0 to 1, 3x to 3, 0 to square root of 9 minus y squared, right? That was our setup. But then we had z, and then we had dz, dy, dx, right? If I want the volume of that solid, all I put here is 1. And then dz, dy, dx. See, by putting a 1 there, what that does is it says, okay, we're going to actually find the volume of that solid you're talking about.
Hey, that's actually really nice.
Yeah, so it's a way to compute volumes of solids. We're not, yeah.
Would it be easier to think of it as like the one is like a constant density function?
Yes, you could look at it as a constant density. And then what is it giving you?
Well, like
It's just-
rho is equal to mass over volume.
So-
So solve for V, which rho is just 1, so multiply both sides by V, volume is equal to the mass.
Yeah. Yeah, in this particular case, that's what you could make the equivalent comparison, I'd say. Oh, I did it on the computer. Okay, so this is it, and we get 3. All right, I'm not going to go into detail about this, but I will at least present it to you. We're not going to do any examples. But everything we just did, remember when I said last class that we had this lamina, right, that had a density function? I said, let's act like that lamina doesn't have any thickness to it. And then I started talking about volume. But how do you talk about volume if there's no thickness, right? Well, it's okay. We're going to fix everything now. Because now we can allow our lamina is no longer a lamina. Our lamina is actually some solid object, E. So if you give me a solid object in 3-dimensional space, and then you provide to me the density function for that solid, then if I do the triple integral over E of the density function with respect to volume, then that gives me the mass of the volume. The mass of the object, E, right? Gives me the mass. And then we have all those other things that we had at the end of class last time. We can find the moment about the xz plane with that formula. We can find the moment about the xz plane with that formula, and then that one for the last moment. And then the big formula is how you get the center of mass. So in order to do the center of mass of a 3-dimensional solid, you have to do a total of 4 triple integrals. The first triple integral gives you mass, right? The first triple integral gives you the mass. Then you have to calculate the moment about the yz plane, the moment about the xz plane, and then you have to calculate the moment about the xy plane. So that's a total of 4 triple integrals. You calculate all of those, and then to find x bar, you take this answer and divide it by the mass. To find y bar, you take this answer and divide it by the mass. And to find z bar, you take this answer and divide it by the mass. And then you'll have the x, y, and z coordinate of the center of mass of the object. All you need is the density function, and you need the solid. As long as the solid's defined and you have the density at every point,